back to here. Okay, so let's get ourselves going for the second half of this. For the second half, what we want to be doing is actually talking about, hey, is it Bagel Tuesday?
Yeah.
I missed Bagel Tuesday. Okay, for the second, remember Bagel Tuesday, Davey?
Yeah.
Okay.
Very easy.
We are going to be joined for the second half by actually one of your compatriots, someone who was in this class a few years ago, was the TA for me for a couple of years, and now is actually applying this same sort of workflow in industry right now. So his name is Dimi Firmakis, and you're going to hear him through the speakers here in just a second. He's actually working in Greece right now and trying to really advance the cause of BIM modeling and energy modeling kind of in the Greek construction industry. So we're going to have him talk to us a little about sort of how we can use some conceptual energy modeling to take a form somewhat like this one that I have over here on the left-hand side and just start doing some very simple energy analysis to it. Because the idea is, as we're going through this, that we have not only an architectural objective we want to achieve in terms of a certain number of square feet, all these different decisions we start making about the shape and form of the building, how it's oriented on the site, all those things actually have an energy impact too. Okay, so it really goes, there's a number of things we need to consider during the conceptual design phase to really optimize our building. So Dimi, I'm trying to think in terms of what we're doing here, like this is the building we have now. Do you have, I'm trying to think if I need to send this to you, or do you have a building we can start with just to get going with the energy analysis, like a real simple, just like a rectangle?
Yeah, the basic conceptual mass I've prepared is pretty simple. The
Sure.
one I showed you earlier today.
Yeah. Okay. Let's go ahead.
Otherwise,
No.
yeah.
Let's just go ahead and do that. I think that'll work out fine. So okay, I'm going to return the screen over to you, and you go ahead and take it, and I'll just kind of keep on kibitzing here along. So let me switch on over, and I have to make Dimi the presenter, who's mysteriously masquerading as Martin Fisher. Okay, so Dimi, go ahead and share your screen, and I think you're taking over.
Yep. Can everyone see my screen?
Not yet. What's going on here? Oh, I know it. Hang on. Do I have to? I'm looking at my screen now. What do I have to do? Oh, there you are. Okay, it stopped. It stopped moving. No, exactly. I was just still looking at my screen. Okay, you are on here. You are now full screen. You have our rapt attention, and I'm going to try and bum a bagel. So, go ahead and take it away. Well, look at this one right over here. You're too kind.
All right. Can everyone hear me loud and clear? Okay. Hopefully you do.
You're doing good, Dini. Go for it.
Okay, so today, as Glenn already mentioned, I'm going to talk to you about how to analyze your basic design at, let's say, the envelope detail level. What you can see here is a design I did. It's basically an office building. Let me show it to you from another 3D view. Get a better hang of it. So it's a pretty big building, but it's very basic shape. So let's see how we can take this building from scratch, get a very basic envelope with it, and let's see how we can analyze it and make it perform better. Okay, so does this look familiar? It's basically the envelope of the building I just showed you. As you can see, it's very basic, a rectangle and another one which basically all I did, I just created a rectangle, and as Glenn already showed you, I just pulled this edge a little bit to the front to kind of resemble the building you saw beforehand. That's
So Dimi, to create that cantilever, did you come up with two rectangles, one on level 1 and another one starting at level 3, or? Yeah.
Yes. So what I did, I created two separate masses. The first one is this, the one I just selected, and which, if I open an elevation view, take this guy away. So the first mass begins in level 1 up to level 3. And the second one, the one that like pops forward, starts from level 3 up to level 6. And which is this guy you can see up here. Which is, as already mentioned, it's a very, very basic rectangle, and all I did, I just pulled this upper front edge like a little bit to the front. And that's all there is to it.
Very good.
And then, like, again, as Glenn like already showed you, for each of those masses, I just added like the respective floors that reflect the levels and the elevations for this one as well, level 3 to level 6. And our design is ready. So we can start our analysis with this like very basic shape. If now you can see like the basic envelope and the mass, like the basic mass floors. So when we start conceptual energy analysis in Revit, you can play around with things under the Analyze tab. You can go to your Energy Analysis tab. Make sure you have like the conceptual mass mode selected, because the latest version of Revit can analyze your actual building model as well. But for now, we're going to do it like at the conceptual level. So make sure like you guys have this mode on.
So just to be clear about that, so what's happening is at the conceptual level, we work with just these forms and these envelopes, and we'll make some assumptions about the surface articulation just in those. Later on, we'll be able to take your more detailed building that has true walls and true windows and switch to building element mode, where it'll do the same sort of analysis but use the true surfaces, as opposed to at this level where we're looking at sort of higher level assumptions.
Okay. Okay, and make sure you have your energy model enabled. And then the first thing to look at is your energy settings. Okay, this window pops up, and we can see like a very short list of like the parameters that we can specify for our project. There are very few common ones, like the type of the building, which you can choose what type of building you're designing. Autodesk offers like this. It's actually quite a varied list of building types. Museums, penitentiaries, post office, universities, schools, and everything.
So,
my building here is an office, so I just picked that.
So, Dimi, what's the impact if we go ahead and choose office, for example, as opposed to a house or a penitentiary? What does that actually change in the model about the assumptions?
Different building types have different assumptions with regards to airtightness, usage. So all of these have like some default values, and as you can see here, the operating schedule default might vary, but in any case, you can change that down here and pick whichever like is closer to you, the building use you guys wanna do. Okay. And it's also the number of people that use the building. So correct me if I'm wrong, Glenn, but I think for the office type, the algorithm assumes it's around 150 people, whereas for a house, it's going to be like 6 or something.
Yeah, it's like number of people per square feet. So even like as we're thinking about a building, we can subdivide it. A classroom is a lot more dense in terms of the number of us and how much energy we're generating than a typical office space, because we're pretty tightly packed in here. An auditorium is even worse because we're all kind of packed in there. But then again, we're not all that active in the auditorium. You know, so it's timing, it's density, it's the level of activity going on and how much energy that might be. Yeah, it's all sort of buried alive in this notion about building type. At a high level, We can control it in more fine detail later, but at a high level, it's all tied up in that.
Yep. And a very, very basic aspect is as well your location, like where your project is located.
Oh, we're
You
in
can
Sag.
specify your location
We're
here.
in Saginaw, Michigan. Go ahead and put us in Saginaw.
So, did everyone see what I just did? So if you go to this section here, there's like this box with like 3 dots, and if you click that, you can basically choose the project location. So you can type here, I don't know, Stanford. Oh, it's still open. Come on. What?
It's all your internet connection. We're using up all your internet.
So I don't know.
That one won't have Saginaw. Go for Detroit if you have that in there.
Or whatever.
Paris, France?
Yeah.
Well, it's getting better. Okay.
Yeah, whatever.
Okay, that's fine.
Okay, Denver, Colorado. And project location is specified. You also determine the ground plane here, which for Revit is very, very essential because everything below this specified ground plane is considered underground. So it actually affects your the results of your analysis. So make sure you specify this correctly. Then we have the energy model assumptions that we might need to take a look at. The first 3, 4 of those aspects are, I think we're going to keep them for later. For right now, I would urge you to basically uncheck this guy here, the perimeter zones. What this guy does, it basically automatically divides the building mass into zones, into usage zones, like where what parts of this mass are being used by people at what distance from the walls and everything.
What?
So right now,
yeah, turn on for a second. We'll see the impact.
Yeah. You see, like.
It's a catching up. There you go.
You see.
Well, it's set back to 0. Go ahead and give yourself an offset.
I can.
Oh, okay.
Sure. So let's give it an offset of like. I think I have it like this. Oh, it's still very low, but yeah, you can see that it did like some zone division over here for this mass and everything, and it also.
Oh, I see. That's very small. Yeah.
Like this. It is, but
Anyways. Yeah. The zoning is really, it's this thing where when we get into more detail, you find that a lot of buildings have, you can think about a separate thermal zone near the windows versus the core of the building. Okay. For right now, what DB's suggesting, I think, is actually a good thing, which is just go ahead and leave that off. Think of it as like just a big open plan office where there really is no interior wall subdividing it up. We'll get to that a little bit later when we start controlling it, the detail. But that often, when we think about buildings, you think about that perimeter being a little different. It's more controlled by the exterior forces than the center of the building.
So yeah, you see, like I think I put a perimeter zone of 5 meters and everything, and you see what Revit did with subdividing the zones and everything. It basically takes 5 meters from the exterior walls and assigns like separate zones for that. But for now, let's take that out. Then we can take a look at in our construction assumptions. We cannot like go deep into engineering here, but it offers like a very good overall view of what we can do and how to approach our construction. So we have like the basic building elements here: exterior walls, interiors, roofs, slabs, glazing. Each of which sections has like a drop-down list with some very, let's say, crude construction. So lightweight construction, mild insulation, typical high insulation and everything. I did like high mass construction with high insulation. Same goes for interior walls, exterior underground slabs and everything. So just go ahead and pick whichever like is closer to what you're like imagining designing later. Also openings and shades and everything.
Yeah. So these all end up computing. They kind of roughly equivalent or are equivalent to different R values for walls, different U values for the window surfaces, and high versus low mass. That's that whole notion of, is it going to retain heat? Is it like a thermal? What is it? Will it help level out the heat over time? Or thin walls, they don't store the heat and re-radiate it through the day. So it's really just sort of a very high level set of assumptions about the type of construction. Again, we'll get into that, how to make that more specific to your construction technique a little bit later. How about this glazing percentage? What's that all about? Because it seems like they put all sorts of windows all over this building. Yeah, how did it come up with that?
Yeah, so what Revit does is by default it sets an automatic window to surface ratio for each of the exterior building surfaces. So is this tour working? Can everyone see I'm rotating around the building?
Yep, looking good.
So you see that, Revit has placed windows all over around the building. And that is because the default percentage glazing is set to 40%. If I go ahead and change that, let's say I want 20% of windows, you see that it automatically changed the glazing area for each of my surfaces. I will show you later how we can customize the glazing area for each of the building surfaces, but for now, this is the default, let's say, approach. You can also play around with the seal height for each of those surfaces. Right now, it's set to 7 to almost a meter high, but you can make it higher, and you see that they moved up a bit. It also offers a very handy, at times, option if you want to shade your glazing, and also the shade depth. So right now the shade depth is around like half a meter, and if I press OK, you see that it automatically adds shading for each of my glazing areas.
They're pretty small to see. You see those little guys? Yeah.
So this is the glazing. If you want higher glazing, you can also adjust the shade depth, and as you can see, it automatically puts like bigger shading for all my windows. Again, I will show you later how to customize these things for your building surfaces.
So at a high level, we've taken this conceptual form and kind of applied some very gross assumptions to it in terms of just overall glazing to wall ratios, some gross assumptions about what the U values and the R values of the wall are. Why don't you go ahead and run an analysis and actually show us what kind of results this get,
Sure.
and we can think about like how that's useful to us.
Precisely. So after you do your basics, go ahead and under your energy analysis tab and press your run energy simulation. Right, and here you can specify the name of your simulation and the name of your project. So right now I'm just going to use like a run for which I've already done under another project. And okay, and we wait for Revit to do its magic. Usually, the simulation doesn't take long. It takes like from a few seconds to a few minutes, depending on the computer and your internet connection.
Okay, so this again is going to go off as a cloud service. It's going to kind of do it off there and report the values back. And as it's doing it, let's just kind of talk for a second about this whole issue of kind of gross assumptions versus very kind of fine articulation of the building surface. Yeah. The idea with this is really, for a lot of things we do in terms of very quick analysis, it actually is sufficient just to say, it's about 50% window, 50% wall, and as we think about heat flowing in and out through those different surfaces, you get some pretty reasonable numbers. They're definitely within the ballpark of where you need to be to at least understand comparatively, is this a better shape versus that shape? Is this a better orientation of the building versus rotating at 90 degrees? It's all good comparative data. Later on, Davey will show we can kind of keep on getting finer and be very specific about how it's articulated on every side and get more and more control. But the idea is to really, if we can take your building shape and within 10 minutes, get some real quick information, that's enough to get us steered in the right direction so we go deeper. Yeah, Sarah, you have a question here?
Yeah, can you get to a point where it can give you energy data over time, like over 5 years of the life of the building, this is how much you need to heat it to cool it, that's how much total energy you're using to...
Sure. Actually, when the report comes up, actually we have a report that we can show, maybe one that you've already run.
The one I just did, it's up.
Oh, beautiful.
It's ready.
Beautiful. Go ahead and walk us through it, and you'll see, Sarah, it's actually part of what it reports.
Okay. So you see that the report that comes out of this thing looks like this. This is like a very short picture of our building. You can zoom in if you want. And then it comes up with a lot of variety of numbers. There's your location and the weather station that's used to analyze the climate data. And the defaults for the outdoor temperature and everything based on that weather station. Also, you can check if you have the right usage. So you see people 149, which comes back to the office usage. And the cost for energy, electrical energy.
Now, just so you know, those numbers are actually, it's looking them up out of a big database somewhere, so it's giving you true numbers for anywhere in the world. It keeps track of the actual utility rates for both fuel and for electricity.
Yep, that's correct. And then we can start looking at our performance factors. A very, very handy and useful number we can look at is the energy use intensity. Revit comes up with 3 numbers for the EUI, electricity, fuel, and total. And the main reason why that's very useful, it's a very good energy metric as it's a per area one, which means, as you see, it's per square meter, which actually comes very helpful when we want to compare projects of different sizes or a bit different square footage and everything. Also, we can see how we're doing in terms of life cycle, and electricity use for the life cycle of the building, energy costs and everything, as well as for renewable potential.
So 30 years.
So this gives us a fair idea of how much kilowatt hours per year, how much energy we can generate if we put PV systems on our roof. You can see here different levels of efficiency. We move on with carbon emissions. You see here the very basic category for our energy consumption and as well for our carbon footprint. Moving down, it breaks down for us the energy uses, which energy is used for electricity, fuel, HVAC, hot water, and everything. Which gives us a very, very good idea how are we using our energy, which chunks of our base or our bill monthly goes to what energy, lighting, electricity, fuel, and everything. There's another very useful chart. It's actually a new one, but I think it's a very good idea that's integrated in this thing. This chart basically shows us how are we doing with our current model. You see our current model is represented by this vertical line under here in the middle. And it shows us how good or bad we're doing for some performance factors. So we see, for example, for the first one, light load efficiency, we're doing okay, but we still have some, let's say, some room for improvement. Our lighting efficiency is not very good, so we can talk with our electrical engineers about it, how we can enhance our plug loads and our lighting efficiency. And you can also see another area that actually should draw your attention is the windows. You see here that we have also some room for improvement. Um, we're doing good in terms of wall insulation and everything else. Also, very useful charts are these monthly heating and cooling loads. What these do is they basically show us where we're losing energy from. We have like this legend to the right that shows us like the categories, and the colors like reflect back to this chart, and we can see which bar actually is bigger.
So Demi, which of the different like areas of the building are we losing the most heat from right now?
So right now, conduction is our biggest problem, which means that we have to do something about our windows. And also in terms of cooling, window solar is pretty big, and lighting, of course, which, as you see, it all reflects back to what we've seen up here, meaning that we need to do something with our lights and with our windows.
So Demi, if Windows Solar was an issue, like what sort of things might we think about doing to sort of improve on that number? Like in the conceptual model, what can we change that would actually bring the Windows Solar load down a little bit?
Shading.
Okay, so the amount of shading on the windows?
Yes, that would be like, let's say, the cheapest and most, the immediate solution that should come up. We can also like look into different window types and everything, but actually that's more expensive. But shading is actually will do a pretty good job as a first strategy.
Could you program in like window glazing that is used, for high efficiency like insulation and stuff?
Oh, so the question was, can we program in kind of very high efficiency glazing? And let's talk about this in terms of there being a continuum. The conceptual energy analysis and the conceptual constructions Demi showed gives you sort of a very relatively limited range of choices. When we actually get into doing the real building modeling, then we can actually be very, very precise about the precise material, the thicknesses, and really drive a U value that you want the window to have. So at this kind of quick get your answer in 10 minutes level, you get 4 or 5 different choices, but not as much variability. But if you take it one step further, we can go to the web and kind of get some more control or really do the true modeling of the finished materials. So Demi, can you compare for us? Oh, actually, very good. Like, go ahead and show in terms of like the conceptual assumptions. Let's take a look at those windows, the mass glazing, and kind of see what sort of options are in there.
Yes, there are quite a few of them. As Glenn correctly mentioned, the assumptions here are very rough. So of course you see like there's a variety of glazing we can use: single pane, double pane. I think there should be a triple one. Yes, triple, or even quadruple. So you can change that, like low E, cold climate, high solar heat gain factor, which is actually much better than the one we just used. We don't use skylights, so yes, you have a few choices embedded in this database.
Sure.
But again, as Glenn mentioned, it's not like the exact thing you want to be using, but it's very, very useful for this level of detail.
Beautiful. So Demi, really one of the things about this whole workflow that's kind of useful to think about is this will give you a number. It'll say, oh, it's going to use $15 million over 30 years. But again, I'm not betting money on that. It's giving you some sense of what it's going to be. It's really more about comparison of different options. So Demi, can you show us a couple like reports side by side that kind of gives us the idea of how you can kind of compare some alternatives? And, what's your question?
Can you run these in like
Yes.
batch analyses where you can iterate maybe through the different types of window glazings and other things as well?
Yes, actually, that is part of what. There was that little report that showed, like where there's room for improvement in the different areas. Turns out every time you submit this, it really submits like 50 different reports that are going in the background. And that's how it figures out which of the things you're at the high end or which of the ones, so it is doing that in the background. we can get to, there's a web interface that lets you see all this, where you can actually see all the different building, all the different options. But what happens when you go through and compare some?
Yes. So I have another analysis on the same building but with different glazing.
Okay.
So which is ready, not to lose time. So let's go ahead and compare those two. Okay. So in this report environment, you can pick the two reports you want to compare, and to the upper left-hand corner, you click compare over here, and boom, it just brings it one next to the other, and you can just scroll down and see the differences between the two. So you can see here, under the same assumptions, okay, the left list is the building I just showed you, and the right one is the building I did. So you can see the difference between the two. You see that my building actually has higher energy use intensity. It goes like up from 151 to 166, and quite higher energy use intensity overall.
What was the difference between those two? That's pretty striking. What got so much worse?
I need to look into the assumptions for that building. I think the glazing was different, and also the insulation of the wall.
Okay. I'm looking at this one. Your window ratio is quite a bit different too. It's 23% on the left and 65% over on the right. So
precisely, it's a very, very. I can actually show you guys that. I can actually show that model then if you guys want.
Oh, sure. Well, go ahead, and we got about another minute or two. So let's go ahead and wrap it and kind of like just give folks an idea where we're going to be going with on Thursday with us.
Okay, so to finish this up, you can compare the two buildings here, and you can see which strategy actually works best. On Thursday, I'm going to show you how to customize the surfaces of your building to actually resemble more towards your design intent, how to add custom glazing and windows, and also how you can add some custom parameters to your surfaces in order to have a more accurate energy analysis.
Fantastic. Okay, let's go ahead and stop there for today. So the idea is really at a high level from top down, just coming up with an overall shape, thinking about it architecturally, but also starting to think about, what is going to be the best shape and form from an energy standpoint, what orientation is going to be best, to try and really get as much information as possible to inform that. And also on Thursday, we'll show you how we can take these just forms, these big blobs of buildings, and actually turn those into real walls, real floors, put real shafts in them, and very quickly go from just sort of this form to actually the shell of a building. Okay, and use that as a starting point for starting to do some more detailed design. So that's what's happening on Thursday. So come on back for more fun. Okay, question over here? No? Okay, good. So Dimi, thank you very much for joining us today. Let me go ahead and we'll sign you off on this side and stop the recording, and we'll answer a few questions.